welcome once again to the lecture module 1 lecture 3 of RF transceiver design. In last two class we have discussed about what are the application and how we can design a complete RF front end. We have also seen the flow of RF front end design or transceiver design and how we can make RF circuits, various modules we have seen. So, in this lecture we will also see basics of wireless communication and some of the basic concept related to communication theory, which is helpful to us for the complete course and understanding the complete RF transceiver design. So, we see general consideration. So, in this let us say when you are trying to call one person to the another person over the mobile. So, how the signal travels, you can analyze by yourself also. I will just give the rough idea that how the signal will travel. So, first your voice signal, which is a analog in nature, is going to be modulated. Once that signal is modulated, then it will be transferred over the carrier. So, the frequency of the voice signal will be 20 kilohertz to uh, 2 kilohertz to 20 kilohertz, and that signal will again be up converted to the carrier frequency of 900 megahertz or whatever frequency that we desired. If we consider GSM, then it is a 900 megahertz. So, when I try to call to any of my friend, then what will happen, that signal with carrier will first travel wirelessly to the base station. So, there is a base station nearby. So, that base station will capture that signal, and let us say if you are trying to call to the Bengaluru, then the base station near to the your friend location will have been connected with the optical fiber, and there is another base station, and that base station will be connected to the wirelessly to the another person. Now, there is a two wireless link, in between there is a optical link. So, there is a combination of wireless and optical links will be there in order to do the complete communication. Again that signal will reach to the baseband, means in mobile, and then it will be reconstructed back. So, this entire process will happen in a fraction of second, even in millisecond of period. So, your call is connected in millisecond of period. So, in this lecture, this is the outline. We try to see the various modulation scheme like AM, PM, FM, which are the basic modulation. There are some ISI, intersymbol interference, what are the constellation diagram, how we can make, what is the ASK, PSK, FSK, some of the advanced modulation scheme. Even we will see, try to see, analyze the OFDM and spectral regrowth. There is a mobile system in which cellular system handoff, multipath padding. So, these are the also we will try to just give the overview. If you want to see, you want to understand more in detail, you need to go to the basic communication theory courses. Some of the wireless standards we will try to look upon, and then there are some multiple access techniques like duplexing, frequency division, multiple access techniques, time division multiple access, and code division multiple access techniques. So, we will try to cover as much in within a 2-3 lectures of basic of communication theory. So, what is this is a generic communication as I told. So, there is a baseband signal. So, this is a baseband signal that let us say it might be a voice signal or it might be a data signal, but it has a certain bandwidth, and it will be lying at a 0 frequency. Now, that baseband signal required some modulation, and that is a modulator you need to use. So, this is a modulator that is used to up convert that signal to the carrier frequency omega c. So, this signal is up converted to the carrier frequency, and the moment you up convert the signal, that is a xt. So, here the signal is denoted as xt at cos omega ct plus theta t. So, here this signal, this is a frequency domain of the same. Here whatever is shown is a frequency domain, this is in time domain. Now, this this signal is again transferred to the omega ct. So, this is the at, because it is at omega c, this is up converted to the carrier frequency omega c, and that baseband signal now residing on the carrier frequency omega c t. So, this is called a passband signal. Instead of this is a baseband signal, and then there is a passband signal, because you have already modulated and up converted the signal. So, the passband signals will look like this, and then that signal will travel over the any medium. There is a possibility that this medium will be optical fiber, or it can be wireless. So, there is a medium or any kind of channel will be there in between, and it will travel over the distance, and again you will get the, because it will travel over the distance, the amplitude of the signal is very less, and the signal it has a many distortion is added, and because of that you need to reconstruct, means the ultimate aim of receiver is to reconstruct the incoming signal. So, you required a demodulator. The first component that is required, demodulator. What exactly demodulator will do? It will this passband signal will be converted to the baseband signal. So, this will be down converted to the baseband signal, and then you will get the signal which is a reconstructed. So, this is a signal that you have transferred, and then this is a signal that you have reconstructed. So, this complete process is nothing but a communication, generic communication, and here in between, so modulator and demodulator, there is RF front end. So, you need to have understanding of baseband as well as a front end, so that you can make a complete system which is a work for various application. This combination of modulator and demodulator is sometimes also called a modem. So, this is a combination modulator and demodulator. So, how the communication happens? So, this is a very basic block diagram of transmitter and receiver. So, we will see that modulation is important part, means as we have seen in the last example also, modulation is important part in any RF design or communication. So, what are the impact of modulation in RF system design? So, here you can see that there is two kinds of signal. In this there is a 101. So, this bit 1 is represented by certain signal, sinusoidal signal at certain frequency, and then there is a 0, there is a no signal is transferred. Again at 1 there is a signal is transferred. So, this is one example, and another example, in this there is a we are trying to send multiple bits, let us say 0 0 1 1 1 0 or 0 0. So, this can be possible. Here you can see this is a 0 0. So, there is a no information. When there is a 1 1, there are both the signal amplitude is very high. In 1 0 there is a signal which is these signals are little bit amplitude is less. So, what is happening that if you try to reconstruct this signal, and if you try to reconstruct this signal, So, the reconstruction will be better in terms of detecting this signal compared to this signal, because this signal has a much more complexity. So, here this can be considered 0 1. So, this uh, this is a 1 0 1 and there are 2 bits that we are transferring. So, how we are how the complex modulation will affect your the complete detection of the signal. So, as you try to add the more complexity in your signal, then in your modulation scheme your detection will be difficult. Another is a impact in the bandwidth. So, the bandwidth occupied by the modulated carrier for a given information rate in the baseband signal. So, let us say for Wi-Fi there is a 22 megahertz of bandwidth. So, various frequency band is using various bandwidth. So, as you try to increase the bandwidth, so it is obvious that in the second there is a higher second example there is a higher bandwidth compared to this example. So, we can easily observe that if you have a wider bandwidth, then the reconstruction is difficult. Then there is a power impact. So, power amplifier design for a linear versus a non-linear. So, if your system has a or your modulation scheme is a linear in nature, then what will happen, you need a much linear amplifier. And again in the reconstruction, if your power amplifier linearity is not much better, then while you try to reconstruct the signal, you will get much distorted signal. So, there is a impact in the power also when we are designing a power amplifier. So, modulation has a much impact on complete RF system design. So, these are the whenever we try to design a communication system or the RF transceiver design, we try to see this basic thing, that is a what is the probability of detection, what is the bandwidth, and what is the impact of power. So, uh, this always there should be in the mind of the RF designer. Now, let us see the some modulation scheme that we try to use in the communication. Amplitude modulation, nowadays in the current century there are limited application, but it is help us to understand many other digital modulation scheme. So, we need to study this amplitude modulation for better understanding. So, how amplitude modulation happen? So, let us say there is some message signal as BBT, baseband signal, and this is a baseband signal spectrum. So, this is a time domain of the signal and this is a frequency domain of the signal, and then you just try to multiply that signal with the certain frequency cos omega ct, AC cos omega ct. So, this is nothing but the multiplying the two signal in time domain. So, convolution in frequency domain. You can denote this AC cos omega ct in frequency as a minus omega c 0 and omega c with the amplitude. This signal, the moment you do the multiplication, the baseband signal will be over the carrier. So, your modulated signal in time domain will look something like this, and your in frequency domain it will be like this, and it can be also denoted as M, which is AC1 plus M SBBT cos omega c t. Here the M is nothing but a modulation index. So, this is a basic amplitude modulation you might have already studied. So, this has a application, and you can also easily understand other modulation scheme as well by using this modulation scheme. There is another kind of modulation scheme that is called angle modulation scheme. So, what will happen that in this we have just changed the amplitude of the carrier signal with the modulated with the baseband signal. but in other in angle modulation, which will play with the angle, which is omega ct plus 5. So, this angle will be changed. So, there is a angle modulation, and angle modulation has a two part, means you can define in terms of it as a phase modulation and frequency modulation. So, these are the special case, phase modulation and frequency modulation are the special case of a angle modulation. So, if angle of carrier is modulated, so let us say your signal ST, which is AC cos omega ct plus theta t, and if this angle is modulated according to the amplitude of the baseband signal, then we will have a variation in frequency or phase. So, your frequency and phase is varying, and you will, the first modulation, that is the phase modulation, in this angle is directly proportional to the baseband signal. So, we can say that your theta t is nothing but m SSB t. This theta t is directly replaced with the m SSB t, and if you try to see that signal, it will have a something different kind of phases at different places. So, only the zero crossing will change. You will observe the change in the zero crossing over the in the time domain. Similarly, frequency modulation, here phase is proportional to integral of baseband signal. So, your theta t, which is m integration of s bbt d tau. So, this phase modulation and frequency modulation and phase modulation is more called as angle modulation, and sometimes this will help. Let us say if you are designing a oscillator or synthesizer, to understand how various phases are added in your output of the oscillator or the synthesizer, this phase modulation plays the important role. There are the term like injection pooling or injection locking. So, this you can understand much better if you have an idea of there is a possibility of angle modulation. So, we have seen the three basic modulation scheme of analog. One is amplitude modulation, phase modulation, and the frequency modulation. So, this was a prior widely used modulation scheme as far as analog modulation is concerned, but nowadays analog modulation is replaced with the uh, digital modulation. So, the basic digital modulation, how it happens, your carrier frequency will remain same. So, if I want to transfer that, let us say beat of 1, then I will just send a 1 carrier signal. If I do not want to transfer the beat with 0 amplitude, it is a, I should make it as a just a blank. So, when there is a 1, signal is transferred, when there is a 0, signal is not transferred. So, this kind of modulation scheme are called ASK, that is called the amplitude shift keying, where we are shifting the amplitude, means we are just keying the amplitude with the whatever amplitude which are coming from the baseband signal. Then another class of modulation scheme, that is a phase modulation, that is a PSK, phase shift keying. So, here what is happening, that your carrier signal, what we are trying to do is to change the phase of the carrier. So, let us say if I have a 1 0, then initially, so in this example you can see there is a no phase, then there is a 180-degree phase shift the moment I have shifted to 0, and again when I will shift to 1, I will have a 0-degree phase shift. So, there is a immediately change in the phase of the signal. When we are transferring the 1, there is a 0 phase, and when we are transferring 0, there is a 180-degree phase shift. So, it can be anything that we have defined for our modulation scheme. So, you can also write the PSK for PSK modulation, AC cos omega ct if data is equal to 0, or AC cos omega ct plus 180 if data is equal to 1. Similarly, you can also write for ASK ASK AC cos omega ct if data is 0 equal to you can write as ASK t equal to AC cos omega ct if data is equal to 1. So, when 1 there is a signal, otherwise it is a 0 if data is equal to 0. So, this is how the ASK will be, and this as we have seen a PSK, in FSK what will happen, that we just change the frequency of operation. So, let us say carrier frequency is f, and then after when 0 will come, it is a f plus delta f. So, there is a variation in the frequency when we are using a frequency shift keying. So, in amplitude shift keying, we are just seeing the amplitude, means we are just changing the amplitude either high or low. In phase shift keying, we are changing the phase of the signal 0 or 180, and in frequency shift keying, we are changing the frequency of signal. So, this ASK and PSK are widely used. FSK is not that much widely used modulation scheme. We will see much more in detail about this ASK PSK modulation scheme. So, now there is one important concept that I just want to add here in digital communication, that is inter-symbol interference. So, in communication system, we will try to consider the linear time invariant system. So, any linear time invariant system, it can distort a signal if they do not provide a sufficient bandwidth. Let us say there is a one system, we can take one example of a RC low pass circuit, or this is called a linear time invariant system. Now, what exactly it is, the bandwidth of this RC filter is not sufficient, it is limited. However, when we are trying to give the square pulse, which is a 1 0, and it consists of many frequency components. Now, when you apply the square signal to the low pass RC circuit, there is a charging and discharging will happen. So, due to this charging and discharging, your actual required signal is square pulse like this. However, in output you are getting the distorted signal. So, there is a basic understanding that a signal cannot be both time limited and bandwidth limited. So, either it will be time limited or either it will be band limited. So, bandwidth limited. So, it can never be a both. So, in this case, when you applied the this has a many frequency component, very wide band signal to the very band limited system, that will distort the signal. So, the time limited passes through the band limited system, the output must extend to infinity in the time domain. So, let us say I will give one example, here there is a 1, after that time 0, again there is a 1, there is a 0, and if this 1 0 1 0 pattern will happen, and if your system is a band limited, then this will increase the this might get the final output at a long time, then another signal already appear. So, again this at this point this signal will be increase and it will reach to the maximum point. Now, in this case what is happening, that your this signal is spreaded on this signal. So, this is one symbol, let us say if this is a one symbol, and this symbol, because of this uh, band limited system, this symbol is spreaded, and because of that spreading, that will have a effect that is called a inter symbol interference. What is happening, that one symbol is interfering with another symbol. So, instead of 0 you will find certain amplitude. So, this has a something like this, it will increase, then there is a little bit change, again it will increase, then decrease. So, the amplitude here, in reality there is a 0 should be considered, but it is not 0, some voltage will be there. So, this phenomena is called inter-symbol interference, and this is happening because of this, the signal cannot be both time limited and bandwidth limited. So, we need to overcome the problem of inter-symbol interference. So, how we can reduce the inter-symbol interference in our system. So, the basic thing, let us say the current signal that we have has a many frequency component, and because of the this frequency many frequency component, here you can see this is a baseband T, and if I will take the power spectral density of same, it is a multiple component, and there is a at different uh, time period it has a different amplitude. So, this is a equation of this SBBT, and its amplitude will AN will change accordingly. So, in this there is one question can be thrown, that if this signal is applied, so if this signal is applied to a low pass filter having a narrow bandwidth, for example the bandwidth of low pass filter is only this much, which is a limited, then what will happen, since the frequency component above 1 by 2 TB are suppressed, the signal experience the substantial ISI. So, here you will have a many frequency component, and that you are just passing through the very narrow band with system, then what is happening, that there is a ISI is happening. Now, from this question you can analyze that why this is happening, because you have a multiple frequency component, and that multiple frequency component is happening because you have added the sharp transition from 0 to 1, it is a digital signal. Now, if we try to give the, instead of very wide band signal, if we try to limit the frequency in the transition, then we can reduce the ISI. So, there is a solution for this, and the solution for this is a reduce the bandwidth of the modulated signal. How we can reduce the bandwidth? Instead of a sharp transition between 0 and 1s, which is leading to unnecessarily wide bandwidth, because we are just doing the transition, due to sharp transition between zeros and 1, which is increasing the wide bandwidth, we should add pulse shaping. So, this is very important phenomena. We do not transmit the signal as a 1 and 0, a transition, sharp transition, we will pulse shape the digital signal. So, instead previously the 1 was looking like something like this, but in this pulse shaping we have made the 1 something like this. So, we need to use the pulse shaping in order to reduce the inter-symbol interference. So, now what happens, if this is a ST and if this is a frequency domain power spectral density, if we try to plot, then initially it has the dotted line is this square wave, but now the updated one, because of the pulse shaping, has a low information on the other frequency part. And now if you transfer to the band limited channel or system, then you will not have a ISI, inter symbol interference. So, this is what is a pulse shaping that we should use in the inter in order to solve the problem of ISI. So, why can't we use the sinc function in the time domain? Yes, we can use a sinc. So, this function is nothing but a sinc function, and that is why can't we use the sinc function in the time domain? Yes, sinc in the time domain gives a brick wall spectrum in the frequency domain. So, if you make a sinc function in time domain, you will have very good sharp in frequency domain, and then all 1 and 0 if you transferred in the sinc fashion, your the waveform is in this example is sampled at exactly integer multiple of TB, then you will have a 0 ISI. So, we will not have any ISI inter-symbol interference if we have a sinc function, means if your signal amplitude is made as a sinc function, then you will have a 0 ISI, and this is called a Nyquist signaling. So, this method of making the 0 ISI is called a Nyquist signaling. So, thank you for today's lecture. We will try to continue with the same theory of communication, and we will go further in the same. Thank you all of you.